So you have 14 units. Now, these units are divided into several areas as general chemistry. The general chemistry portion include chapters, the units 1, 2, and 3. And then there's another section which is physical chemistry. Physical chemistry comes in kind of two parts. Part 1 includes the units 4 and 5, and the physical chemistry part 2 includes the units 11, 12, and 13. And then we have inorganic chemistry. This is unit 6. And then the most dreaded organic. This includes the units 7, 8, 9, and 10. And then the industrial. This is the final unit. So that is more like the breakdown of the units in your syllabus. So just let me know if you cannot see why, as I talk, if you cannot see what I'm saying, just send me a note or just unmute yourself and let me know. Okay, now let's see if I can show you some resources that would be useful. Now, when it comes for learning these A-level subjects, it's important that you actually read a little bit outside of your resources. Like I have sent you the resource book, which is actually downloaded from the NIE website, the National Institute of Education. So you can go to their website and download all the other resource books for all the subjects that you are doing. And in addition to that, it is helpful if you're reading some additional books so that you can expand your understanding about these topics that is discussed in the syllabus. So one free resource you can use is OpenStax. I think you can again see a website, a web page that I'm showing here. So let me write the web address. This is OpenStax. So you can, I think you can see it here. It's openstax.org. So in here, you can find under subjects, you can go to sciences. This is not just sciences. If you have any friends who are doing like commerce, they may be able to find certain books that fits there. So here you can see a couple of chemistry books. The only difference is that the way they have lined up the topics. So you can actually go and download the whole PDF book. And when you read this book and the resource materials that I have sent you, you will realize that the NIE resource book is actually mostly developed through this book. This is a book that is used in many universities worldwide. So yes, the resource book you got from me is also developed from this. The professors in this country also use these books. They don't tell it, but they use it. And that is one resource I wanted to show you. So you might have seen there are books for biology, there's books for physics. So you can check those things as well. And then I'm going to show you another resource that you can use. Now, this one is a site for simulations. I can't find it. Now, this website is the PhET simulation website. I believe you can see here it says PhET. If you go to Google and type PhET, you will come up with this website. If not, let me write. Here you can, I don't know if you can see it well or not, but it is phet.colorado.edu. So that is the web address of that. Now, why this is going to be useful, it has a lot of simulations that will help you to visualize certain things. When we talk about chemistry, you know, you don't see the atom, but then you have to visualize things, how the electrons move, how the bonds are made, what kind of bond angles you're going to see. So let's see. All right. So here you can find under simulation, you can see there are simulations for physics, chemistry, math. So since this is chemistry, I'm going to the chemistry tab. And you can see a lot of simulations. Some might be not relevant for your level, but as you move on, especially in the second unit, you will be doing about molecular geometries, the bond angles and the shapes of molecules. Now, this is a very good resource you can use. It might take a while to load. All right. Here you can see you can move around the molecules, you can add bonds, and you can visualize the bond angles, and you can rotate the bond around and see how the bond angles change as you change the number of bonds. So these items you are going to need when you go to the second unit of this syllabus. So just showing you some resources you can use that will help you to improve your understanding. Okay. Now, some people who are doing chemistry or the sciences in English medium worry a little bit that they might fall back, but my opinion is that you are very much advantaged. You are actually advantaged compared to the students who are taking this in Sinhala medium. The issue with Sinhala medium is that the subject is translated to Sinhala, and that chemistry written in Sinhala is actually hard to understand. But for you, it's not very hard, because the language is more or less like the everyday language you use, more common language. But that Sinhala translation is not the average Sinhala we use. So actually you are at an advantage when you're doing English medium, especially chemistry, because comparing chemistry Sinhala version and English version, even I cannot understand what the Sinhala version is saying. I have to read the English one to understand what exactly the Sinhala one is saying. So you are at advantage. Right. As for the syllabus, now your O-levels was delayed. Just because of that, we cannot assume that your A-level is going to get pushed back. We'll just assume that it's going to be held in the regular time by August 2024. So I wish to finish the syllabus by end of March or by April. So In order to do that, I plan to hold more extra session. If I'm holding extra sessions, I'm not going to charge any additional fee. Since this is online, we can settle down for a suitable time that works for majority of you, and we can do that. So once we finish the syllabus, I actually plan to go over the revision and also past papers. Yeah, so another suggestion, it's my personal opinion that if you are doing A-levels and if you don't have much idea what you are going to do after A-levels, I would suggest that you all go to the UGC website, the University Grants Commission website. Let me see if I can pull it out. This is ugc.ac.lk. So when you go to this website, you can see under university admissions, there's a drop-down menu. There's this admissions handbook. I know many people look into this admissions handbook once they get the A-level result, but my recommendation is that you can go to this, download this admissions handbook and see what kind of programs there are. Maybe you will fall in love with a subject area that you have never heard before. So that way you can make better choices. And also make an aim just to pass the exam in your first attempt and get admitted into a program, because my opinion is that in Sri Lanka, there are plenty of opportunities available to you. The only issue is many students are not aware about these opportunities. You can actually be a scientist, even if you have 3 S's, still you can be a scientist if you want, that's your want. So we have something called Open University. Many people don't consider it, but I personally know people who went to Open University and currently working in the United States as scientists. So it's a very good resource, and be aware of what we have in Sri Lanka before you try to skip exam or try for a second attempt. Just aim for the first attempt and make a better decision for yourself. Okay, now let's start our lesson. We'll go into the actual content. Again, if you cannot hear me or if you cannot see what I'm sharing, just let me know, or if not, you can open your video and let me know that you cannot see your whatever it is. So today, what I'm planning to go over is this first part. So this first part I'm planning to go over, and this is about 6 periods according to the syllabus, but that means it's pretty much around 4 hours. Let's see how far we can go with this content. Okay, so if we really think about everything around us, everything around us can be divided into 2 broad categories. So maybe I'll write as universe. Universe we can call, it's made out of 2 things. One, it's energy. The other one is matter. Now, chemistry is the branch of science that study about matter. So this is chemistry is all about. So now, what exactly is matter? You might have heard this definition before. Matter is anything that has a mass and that is going to occupy a space. Anything that has a mass and occupies space. Now you see the word here, mass. I just want to clarify that mass is very different from weight, even though in general communication, we use mass and weight as the same thing. Scientifically, they are not. Mass means the amount of matter or the amount of material, but weight means how this amount of matter feels the gravitational force. The reason I want to mention this is that as you go on, you will keep on seeing this word mass all the time. Okay, so just to clarify what the difference between mass and weight. Let's say we have this man in the spacesuit. So it's like a closed system because he's in a very tightly closed spacesuit. Even if he breathes, whatever the air he breathes out, it's still inside whatever the packing he has. And let's say he's sweating, even that single drop of sweat is trapped inside there as a matter. So let's say this guy's mass on Earth, it is 100 kilograms and weight is 980 newtons. And immediately we drop this person on the moon. And you know, on moon, our gravitational force is like 1/6 of Earth. So you can see the value for mass didn't change because that is the same amount of matter. Just imagine, or you can imagine, we are putting 10 coconuts into a sack. We put 10 coconuts. No matter where you take that sack, you still have 10 coconuts in it. But if you take that 10 coconuts to the moon, it will weigh different. So it's just a matter of how material feel gravitational force that will define weight. But and then states of matter. You know the basic properties of the 3 states of matter. We have liquid, solids, and gases. Now, how they get these properties like fixed shape and fixed volume, how do they get it? That is basically in the molecular level. Now, this is what chemistry is like. As you go in chemistry, you will get a whole section about gases. You will be doing about gas laws. The reason is the molecular arrangement in these 3 states of matter is very different. In a solid, your atoms or molecules, they are very tightly packed. That is why they are going to have a fixed volume and a fixed shape. But in a liquid, compared to a solid, you can see these particles are less tightly packed. That means the particles, the atoms or the molecules, they have some freedom to move around. So that is why liquids can actually take the shape of a container. And when it comes for gases, they hardly have any packing nature. And this is why we can compress and expand gases. So we are going to look into these different aspects as we advance through these units. So keep in mind, actually, it's very simple. Chemistry is study of matter, and then we are going to break down matter into small different sections and try to understand how they behave and why they actually behave like that. So if you really think about what matter is made out of, is with elements. There is a huge diversity around these matter around us. For example, here you can see we have solid stuff, we have liquids like the river you see here, and we have gases like the clouds here, and we have animate and inanimate things. But all these things are made out of very fewer number of elements. Actually, it is less than 100 elements. So less than 100 elements give this kind of a huge diversity. So how does that happen? It basically happens the way they combine, how many atoms combine together, how they pack together, how one interact with the other one. So that is what gives us this huge diversity. Now, even though we have this periodic table and a lot of elements in it, we don't go over everything in this syllabus. We know that some of the elements like these ones are not very stable, and they are, you actually don't learn about these things in your A levels. So that is why we say that everything results with less than 100 elements. Okay, so here I'm going to put a brief summary of the evolution of the atomic theory. Now, throughout the history, people tried to figure out what exactly is matter. What is it made out of? So in today's lesson, I expect to go all the way from this point to here until Niels Bohr, because this part, I don't think I can get to that point. This is, their names come in the second part of this chapter under the wave properties of material. So first, we are going to look into this part. Now, something about this section is that you usually get, not always, usually get one of these names in your exam paper. So this is just the beginning for you learning this content. But as you go and reach towards the very end of the syllabus, there's a good chance you are going to forget these names. So it is better if you make a small poster or a small paper, hang it somewhere you can see it regularly, so that you are not going to forget the names as you advance through these topics. All right. Now, since the beginning, people were curious. They wanted to learn about what things are made out of. And there were, in ancient times, philosophers. Now, these guys are philosophers. They didn't do any scientific experiments. What they did is that they observed things and they analyzed it. They didn't run any experiments. They just, by observing things, they gave their opinions. So one such philosopher who gave an idea about matter is Empedocles. So Empedocles said that the matter, every matter is made up with 4 basic elements. So he said there are 4 elements. Those 4 elements were fire, water, earth, and air. And then another philosopher named Democritus, he proposed that the matter is made out of tiny, invisible, and indivisible particles. So his argument is that matter is made out of these invisible and indivisible particles. This indivisible in Greek means atomos, and that is how we originated with the idea, the name for atom. So those are the early thoughts. So the first person to propose this indivisible particle concept is Democritus, but he never did any scientific work. All right. Later, there were more philosophers to name, like Plato and Aristotle. These are very famous ones in Europe in those days. Now, when the issue is, these 2 philosophers said that there cannot be such particle as an invisible, indivisible particle. So what Plato and Aristotle said is that there cannot be an indivisible particle. So no indivisible particle. So Plato and Aristotle were like huge names back then. And when these guys said that there cannot be such particle, people believed it. And people actually believed it for thousands of years. So after Plato and Aristotle, the first person to come up with this invisible particle is John Dalton. Now, if you want to take notes, you can write down. So the ideas that John Dalton brought up are named as Dalton's postulates. So in your syllabus, after Plato and Aristotle, the next name pop up is John Dalton. But before John Dalton, there were some other scientists who did experiments, but their names are not mentioned in your syllabus. So how John Dalton came up with his postulates is like a combination of the previous work. He combined what other scientists did before him, and also Dalton himself did few experiments. And with that, he came up with 4 main points. So under this Dalton's postulates, you will see 4 main points. If you read into other books, you might see 5 points or maybe 6. It depends on how people break down these topics. But in your syllabus, this syllabus has broken it down only to 4 points. So the first postulate is that the elements are made out of extremely small, indivisible and invisible particles. So he came back to Democritus' idea about this atom. But by now we know that there are subatomic particles like electrons, protons, and neutrons. So by now, his first point has gone wrong. But back then, this was a huge thing to come back to this indivisible particle and calling it atom. The second postulate is that all atoms of a given element are identical in mass and size. And the atoms of different elements are going to be different. So in some books, they break this as 2 points. That's how you end up with 4 or 5 points. Now here, they have summed up two sentences, kind of 2 phrases as 1 point. So what this actually say is that, let's say we have copper metal as an example. If we look into copper metal atoms, what this first part say is that the atoms of an element are identical. That means this first copper atom is identical to the second copper atom, identical in mass and size. That's what he said. Let's take another metal, another element. The first gold atom is identical to the second gold atom in mass and size. That means both gold atoms have the same mass and same size. And what is second part? The second part says that the different atoms of different elements are going to be different. What that means is that if you compare a copper atom with a gold atom, now if you compare these two, now they are different. They are different from their properties. They are going to have different masses and different sizes. So that is what this second part of this postulate means. But by now, we know about a thing called isotopes. What are isotopes? I believe you have learned them in your O-levels. Isotopes are atoms of the same element. They have different sizes. So with the discovery of isotopes, his second postulate also went wrong. You can see here the carbon atoms. They are all carbons, but they have different masses. So by now, we know his second postulate is also gone wrong. Let's look at the third postulate. In the third postulate, he says that atoms can be neither created nor destroyed. That means you cannot create or destroy an atom. So that means when we do a chemical reaction, let's say we are starting with carbon and oxygen. These are our reactants. So we start with these reactants, and on the other side of the equation, you know, we have products. And you can see we start with carbon and oxygen, and we end up with carbon and oxygen. So the elements we start with are the same elements we end up with. They can be combined in different ways. Their connections can be different, but still the same element. So in other words, if I try to show it like this, carbon and oxygen combining, you cannot suddenly convert a carbon into a hydrogen. So this kind of thing cannot happen. This doesn't happen because we do not create or destroy atoms in a chemical reaction. So that is his third postulate. Okay. The fourth postulate is about compounds. According to this one, he states that compounds are made by combining atoms from different elements in simple whole number ratio. So you need atoms, at least 2 or more atoms from different elements, 2 or more atoms from different elements, and then combine them in simple numerical ratio. Let's see an example. Let's say we have carbon dioxide making reaction. We combine carbon with oxygen and we get carbon dioxide. Here you can see carbon to oxygen ratio is 1:2. So we have different elements. Our two different elements are carbon and oxygen. And we have 2 or more atoms. We have how many atoms? We have 1 carbon and 2 oxygen. So we have overall 3 atoms. And we have combined them in a simple numerical ratio. So this is what his fourth postulate means. We'll take another example. Now this time we are making carbon monoxide. If we take carbon monoxide, you can see the ratio of carbon to oxygen is 1:1. So this actually says you have to use different elements. What will happen if you use the same element? Let's say if you use same element, will you get a compound? Let's say I'm combining oxygen with oxygen. That will give me O2 gas. Now, is O2 gas a compound? No, it's not a compound. it's still an element. If you have the same bunch of atoms, it's an element, the same type of atoms. So that is why you need different elements. You need to combine atoms from different elements. However, by now, his fourth postulate also gone a bit wrong, because there are certain compounds that may combine in very complex ratios. It is not going to be as simple as this. Sometimes there are very large numbers, or maybe even fractional numbers. I have worked with a compound that's formula is written as this. So sometimes we can end up with very complicated numerical ratios. So even this postulate has gone wrong by now. But back then, these were huge discoveries. Okay. So let's kind of try to summarize the main points in Dalton's postulates. So his first point is about elements and atom. He defined what an element is. Element is made out of one type of atom. So, and then he said what an atom is. Atom is an indivisible particle. So that is his first point. And then his second point is about the properties of elements. So basically, if you have same element, what he said is, if it is same element, that means you have same size and mass. If you have different elements, then you're going to have different sizes and masses. His third point is that about that matter cannot be created nor destroyed. It is neither created nor destroyed. And his fourth point was about compounds. So it was about having simple numerical ratios when forming a compound. The next name that we come across in this syllabus is Johnston G. Stoney's name. So what his name associated with is the naming of the fundamental particle of electricity. He named the fundamental unit carrying electricity as electron. So what he basically did is giving a name to the fundamental particle or fundamental unit that carries electricity. So sometimes students get confused that this is the guy who discovered the electron. No, Johnston G. Stoney is not the person who discovered electron. It's J.J. Thompson. We give that credit to J.J. Thompson. So what Stoney did is that giving a name to the fundamental unit of electricity. Now we are going to look into some experiments that were done using electricity. Back then, by this time, electricity was known and people were doing many different types of experiments using electricity. One type of experiment that was done is the cathode ray tube experiment. So Sir William Crooks, this scientist, what he actually tried to do is he tried to see if he can pass electricity through vacuum. And also he tried to see if he can pass electricity through air. Now we know if we want electricity, we need wires. It just doesn't go from thin air. So what he tried to do is he made this big empty space between a cathode and an anode and see if he can pass this electricity. See, this is like an open circuit. He tried to see if he can pass it through this empty space. So what he did first is that he took a tube like this and he had two metal plates. One is cathode. The reason we call it cathode is because it is connected to the negatively charged end of the power supply. So cathode has a negative charge. And the anode, it is connected to the positive end. So that is going to have a positive charge. And when he provided very high voltage while maintaining a vacuum, so he's pumping out air from this. When he pumped out the air, created a vacuum and provide a very high voltage like 10,000 volts, he kind of saw that there is some sort of a particle moving from cathode to anode. So he saw something moving from cathode to anode. Since it was moving from cathode to anode, he called it as cathode rays because as he saw it, these rays originated from the cathode. Now the thing is that these cathode rays are invisible. So when he first did it with vacuum inside the tube, he didn't see green rays going from cathode to anode. He just observed that there is something happening there. So in order to visualize it, he put different gases. And also he started coating this glass tube with inflorescence material. When he filled gases, it is then actually he started seeing these green beams. So cathode rays, they are invisible. They are not green color. The reason we see the green color is at a later point, he filled a gas in here. So he filled a gas. If you want to think, you can think about hydrogen. Let's say he filled hydrogen. But this gas is under a very low pressure. So the gas is under low pressure. And what happens is that when these cathode rays, when they move from cathode to anode, the cathode rays hit the gas molecules. And when that happens, the electrons inside the gas molecule, they become excited and de-excited. It is that excitation and de-excitation that gives this green light, not the cathode ray. All right. Now, William Crooks is not the only person who was working on these kind of cathode ray tubes. There were a lot of people doing many different types of experiments with these cathode ray tubes. Now, J.J. Thompson modified this cathode ray tube in a way that there is a hole in the anode. So the difference is that instead the previous guy, you can see there aren't any holes. This is the basic layout of his cathode ray tube, William Crooks cathode ray tube. But J.J. Thompson made this hole in the middle of the anode, and additionally he had additional stuff attached. He applied a magnetic field. So this is the magnetic field. So you can see the magnet. And then he also provided an electric field. Now these plates, this negative and the positively charged plates, provide electric field. So what happened is that when he provides this high voltage between cathode and anode, he started noticing these cathode rays moving from cathode to anode. And since there is a hole, now whatever the parts of cathode rays that is not absorbed by the anode goes through this hole. When it goes through, he turned on the electric field. First, he turned on the electric field and he noticed that this cathode ray actually tilt towards the positively charged plate. So this cathode ray here, it actually tilted like this towards the positively charged plate. So what does that mean from general sense? The opposite charges attract. So if something attracts towards the positively charged plate, that means that something should be negatively charged. So he deduced that this cathode ray must be negatively charged. And he didn't stop there. Now the way this research goes is once you have some sort of observation, you try your best to confirm it. Next, he removed the electric field and he provided this magnetic field. When he provided the magnetic field, this cathode ray, it deflected in a way that a negative charge would deflect. Now here when we state that, we are very careful to say that in the presence of a magnetic field, the cathode rays deflect in a way a negative charge would deflect, because we are not saying it's deflecting towards north end or south end. It's not. The direction you can basically figure out with your left hand if you take your first 3 fingers in these perpendicular angles, but that is more like a physics concept. So I'm not going to go into details of that, but I kind of have a video. I probably have sent a link to you of that if you have contacted me way before this. So that is a physics part. I'm not going to explain why that happens, but we are careful to say that in the presence of a magnetic field, cathode rays behave like a negative particle. Now, let's go and see how these experiments can be done in our labs. So you will probably get the opportunity to do some of these, or hopefully all of them. So you can see when we turn on power, you can see that there is a certain glow. It's going from cathode towards the anode. Anode is somewhere here. And when we place an object in the path of these cathode rays, now we are going to place an object in the path of the cathode ray. You can see that it's going to create a shadow. Now, this is not a distorted shadow. This is like a very sharp shadow of the object. So from what you observe, now this is your observation. You observe that when you have an object, the path of the cathode rays, you can create a shadow. And what that basically means is that the cathode rays are moving in a straight line. So our inference is that cathode rays, they travel in a straight line. And then another way that J.J. Thompson did this experiment is using charged plates. Now this is one plate up here, and you can see the other plate down here. When we have this cathode rays moving like this, and we have not turned on these plates. When we don't turn on the plates, you can see the cathode rays are moving in a straight path. But when we turn on the plates and provide a positive charge, now we are providing a positive charge to this plate. When we provide it, you can see this cathode ray, that beam, is going to tilt towards the positive charge plate. Now, this is exactly what J.J. Thompson did. So with that, our observation is that the cathode rays are going to deflect towards the positively charged plate. And from that observation, we can conclude that the cathode rays are made of negatively charged particles. Cathode rays are negatively charged particles, and we made to that conclusion by this observation. Another type of experiment done with this is that we place a paddle wheel in the path of the cathode rays. Now these paddle wheels, these plates are coated with a fluorescence material. I mentioned that cathode rays, they don't have any specific color or anything like that. They're basically invisible. The only reason you see color is that these are coated with fluorescence material. When that invisible cathode rays hit the fluorescence material give a color. That's why you see a color. So let's see what happens when we turn on. You can see how fast this paddle wheel spins. It spins very fast. Now, if there isn't a force, it cannot do this. Now, you might have seen windmills or turbines. If you want to spin it, you need to put some sort of a force. Just standing in still air, it is not going to spin. So with that observation, it was possible to conclude that these cathode rays must have some sort of a momentum. In order to have a momentum, there should be a certain mass. There should be a particle with a mass, and there should be some sort of a kinetic energy transfer. So in this experiment, our observation is that the paddle wheel is going to spin. And from that, we can conclude the cathode rays have a momentum. If not, in some places, they said that the cathode rays have a mass and kinetic energy. So you can say it either way, either it has a momentum or a mass plus a kinetic energy. Now let's see how this is going to work in the presence of a magnetic field. You can see that when we hold a magnet, it's going to deflect. Can you see? It is not deflecting towards the magnet. It is deflecting towards an angle perpendicular to it. And if you hold the magnet parallel to the beam, it's not going to deflect at all. So holding the magnet, giving a magnetic field parallel to the cathode rays is not going to cause any deflection. The deflection occurs only if you hold it perpendicular to the beam. So this is the beam. You're holding the magnet perpendicular, and the beam tilts, deflects towards a perpendicular angle, not towards or away from the magnet, a perpendicular angle. So our observation is that this cathode rays, the direction of the deflection is similar to the deflection of a negative charge. So what do we conclude from this observation? We say that the cathode rays are composed of negatively charged particles. So again, both electric field and the magnetic field study, they both come to the same conclusion, that the cathode rays are negatively charged. All right. Now, J.J. Thompson didn't stop from there. He did some additional work too. He went on changing the cathode material. That means the metal used for this cathode. Let's say we make this cathode with copper metal and repeat all the experiments that we just went over. When he did that, there was no change at all. And let's say next time he's changing this cathode, instead of copper, now he's using iron. Let's say he's using iron. Again, repeat all the experiments. And still, he sees the same observation. And then he didn't stop from there. He ended up filling this tube with different types of gases. So at one time, he do it with hydrogen. Next time, he will do it with oxygen. Another run, he can do it with nitrogen. So no matter what gas there was in the tube, again, there was no change at all. So that made him conclude whatever this cathode ray, it is like a particle that is unique to all matter. So therefore, we give him the credit of this credit for the discovery of electron. And all these things are more like qualitative observations, like qualitative results. He was not only able to qualitatively do these assessments, but also he discovered a very important quantitative measure, which is the charge divided by mass ratio. So this is not the only experiment he did. He did some other experiments too. They are not in your syllabus, but what you are supposed to know that he found the EM ratio. For this, he was given the Nobel Prize. And also the credit goes for him for discovery of the electron. So he figured out the EM ratio. Now, let's sum up the properties of cathode rays. The cathode rays, you have seen, they travel in straight line. How do we know that? It's going to make shadows. And then the cathode rays, they have a momentum. They can spin a paddle wheel. And cathode rays, they are composed of negatively charged particles. Why? Why did we say that? Because they deflect towards a positively charged plate. And also, finally, we know the nature of these cathode rays that does not depend on the nature of the gas in the tube or the nature of the cathode material. So it does not depend on the gas in the tube or the cathode material. So these are the main takeaways of this experiment. So this is a very important experiment. You are required to know the observations and what their finding is. And the last part is that the EM ratio. So J.J. Thompson, he found the EM ratio, and the EM ratio is same for no matter what type of gas you use or no matter what kind of cathode material you use. The EM ratio is always the same. It didn't change. Okay, so with all these findings by J.J. Thompson, he proposed a model for the atom. This model is called as the Plum pudding model. Now, in the Dalton's postulates, I forgot to mention, Dalton's model of atom is called as the golf ball model. Let's see if I can. So Dalton's model for the atom, we call it as the golf ball model. Now, why do people give these kind of common names like golf ball model and plum pudding model? So in order to give an idea, now he came up with a lot of scientific points, but not everyone can understand it. An average person cannot understand what an atom is with his postulates. So he brought the golf ball as a model. And golf ball is something pretty much every European person have seen. So when he shows a golf ball and says atom is like this, but only it is invisible, then people understand. So that's why Dalton brought up the golf ball model concept for the atom. And then J.J. Thompson brought up the plum pudding model. Let me find where I... So J.J. Thompson, in plain words, for a layperson to understand, he said the atom looks like a plum pudding. In British or the European cultures, they make a dessert with plum pudding, plums and raisins, nuts, which is pretty much like a Christmas cake. So this is what another idea I can bring up. It's more like a chocolate chip muffin. So what he said is that the negative charges are like plums or like these chocolate chips in this chocolate chip muffin. And the negative charges are embedded, or it is dipped in a whole positively charged matrix. There is a positively charged matrix, and the negative charges are like islands or certain specks in that positively charged matrix. Now, why did he brought up this positively charged matrix? Now think about matter all around you. Matter around you, is it electrically charged? Let's say you touch your pen or pencil. Do you get electrocuted? No. So we know that material around us, matter is electrically neutral. If something is electrically neutral, and if this something is generating negative charges, then there should be equal amount of positive charges to neutralize it. So it's just using simple logic. What J.J. Thompson discovered is the negative charge. He found that there is this negative charge in every material, every matter has a negative charge, but it doesn't electrocute us. So then there should be an equal amount of positive charge. So that is why and how he came up with this idea about the structure of atom. And for a lay person to understand it, he gave the name plum pudding model. The next important name that we come across is Robert Milica. Now, this scientist did an experiment using an oil drop. Now, this is a very interesting oil experiment, because just imagine finding the charge and the mass of electron using an oil drop. Now, in your syllabus, it doesn't go into great details about the experiment. But anyways, I will explain how he did it in simple terms, because it always fascinated me how on earth a person can find the mass and the charge of an electron with an oil drop. Right. So you might have used spray bottles. When you spray something, you can see tiny droplets are made. Let's say you have a way to measure the weight of one droplet. So Robert Millikan had done previous studies to measure the mass of one tiny droplet. And he made this droplet pass through a small slit like this. And when it drops, now things drop because of the gravitational force. Now, because of the gravity, this oil drop is going to fall. This is gravity. And when it drops, what he did is he sent X-rays. There is an X-ray source here. He shoots X-rays towards this X-ray towards the oil drop. What that does is that X-ray is going to knock out an electron from the oil drop. So when an electron is kicked out from the oil drop, this oil drop gets a positive charge. And then he provided an electrical charge. He provides a negative charge to this red top plate and a positive charge to the bottom blue plate. And then he connected the power source, and he can measure the voltage from here. And just imagine when he provides this voltage, now this positively charged oil drop falling under gravity is getting attracted towards this red plate, which is negatively charged. So now he adjusts the current until this positively charged oil drop floats in midair, that it stays still because the gravitational force is equal to the electrostatic force. So this is electrostatic force. Now the gravitational force is equal to electrostatic Now in physics, you will learn that gravitational force depends on the mass. And the electrostatic force is going to depend on the charge and voltage. Now I mentioned Milica had previously measured how much mass the oil drop should have. This is the mass of the, so he has measured this mass. And then he can measure the voltage from this voltmeter. He has, this gives you the voltage. So when you know 2 terms out of 3, now he can find the charge of the electron. So that is how he found the charge of the electron. And then he didn't stop there. He was able to find the mass of the electron as well. He went on to find the mass of electron. Now I mentioned you don't need to know the setup of the oil drop experiment. I'm just showing it so that for out of curiosity, if you're wondering how one can determine the mass and charge of the electron. So previously, J.J. Thompson, if you can recall, he found out what EM ratio is. He found the numerical value for the whole ratio, which is this. This is what J.J. Thompson found. And now Milica found this. Which is the number we had earlier. So substitute that number, which is 1.602 10 to the power -6. So this is coulombs. So do the math, you will get divide this gives you the mass of electron. So isn't it interesting? Actually, a very simple calculation. So you can see the mass of electron is actually a calculated value. It is not a directly measured value. It's a calculated value. Now this number, if I have to write a numerical value, this is going to be 9.1. That is the mass of the electron. So now we have some numbers. Now these scientists, not only they observed some qualitative things, they were able to quantify and do additional calculation and get an actual numerical value for these things. All right, so much later, they found that the mass of electron is nearly like 1 out of 18,000 of an hydrogen atom. So let's say we take one hydrogen atom and divide it by 1837. So if you divide the mass of hydrogen atom by 1837, then that value is equal to the mass of the electron. And by now, we know what is the charge of the electron. We know the charge of the electron and the mass of the electron. Now this is the mass of the electron, and this one is the charge of the electron. So let's say if the charge of electron, if we write that as this, what do we write as the charge of electron as a negative one? For O levels, you might have done that. You know that the charge of electron is, we call it as -1. So what exactly is that? If Milica found the charge of the electron as 1.6 into 10 to the power -19 coulombs, what is this -1? Now these are two different types. This -1 charge is what we call as the relative charge. Then what is the other one? This number is what we call as the absolute charge. Now, when you see these two numbers, it is a lot easier to use this -1 instead of a numerical value with 10 to the power -19. So when it comes for chemistry calculations, we sometimes simplify our numerical values because it is a real pain to deal with a number like 1.6 into 10 to the power -19 and always use it in calculation. So that is why in chemistry, you will find a lot of relative numbers, a simplified version of that very complicated number. All right. Now, people didn't stop from here. They kept on working with these cathode ray tubes, and they did many changes. Another person that did small alteration to this cathode ray experiment is Fujian Goldstein. Now, what he did is that he took a cathode ray tube like this, and he put his anode which is the positive end to the power supply. You connect that to the positive end of the power supply. And then you have the negative end. Instead of placing the cathode in the far end, you can recall in the previous setups, the cathode and the anode were in the far end. Instead of placing the cathode in the far end, what he did is that he placed it, somewhere in the middle area. So instead, he placed it somewhere here. So this is the anode, and here you have the cathode. And it is not just a plain cathode. He placed a cathode with holes. For some reason, he wanted to place a lot of holes in this cathode. Now, he filled this tube with a gas at low pressure. So he filled it with a gas under low pressure. And then he supplied a high voltage. And when he did that, he noticed the regular cathode rays. So the regular cathode rays started from the cathode and they moved towards anode. But at the same time, he saw some other types of rays moving through these holes towards the end of the glass. He saw some other type of rays moving like this and create some sort of a glow, like a brightness on the other end of the tube. Now he thought, as he saw it happen, he thought the purple rays that I have marked, he thought that they are originating from the anode. He thought they are coming from here and going through like this. So he called it as anode rays. And also the anode is positive, so he called them as positive rays as well. And also he called it as canal ray because there is this huge part of the tube or the canal. So he observed these rays actually in this canal part or that other empty part of the tube. So he ended up calling it canal ray as well. So what exactly happened? How did these canal rays occur? So what happened is that when the cathode emits cathode rays, when the cathode emits these cathode rays, the cathode rays goes and bump onto, it's going to hit gas molecules. I mentioned there is a gas. There are gas molecules, gas atoms in this tube. So these electrons or the cathode rays come and hit the gas atoms or the gas molecules. This causes this gas atom to lose an electron. One electron coming from the cathode bumping onto the gas atom makes the gas atom knock out an electron. So what does that result in? When this gas atom or the gas molecule lose an electron, the gas molecule become positively charged. Now all these gas molecules become positively charged when the cathode rays hit them. So when they become positively charged, what do you think that happens? We know our cathode is a negatively charged end. Our cathode is a negative charge, so these positively charged particles, they get attracted towards the cathode. Since the cathode have holes, where there's a hole, this positive charge is able to go through and hit. And that's what caused this glow. So he actually discovered the positive rays or the positive charges. Right. Here you can kind of see it a little bit more clearly. You can see that there is a cathode with holes, and there's a gas under low pressure, and we have the anode. You can see they are connected, the anode positive end, the cathode is connected to the negative end. See, when the cathode rays goes and hit gas molecules, it becomes a positive charge and it can go through the cathode. Now, the same type of experiments done for the cathode ray tube were done for these as well. So that you can recall the types of experiments that's done for the cathode rays. They did it with electric field, they did it with magnetic field, and they placed a paddle wheel. So these type of different experiments were also done. And they were able to identify the properties of the canal rays. I think I should have put underline. Let's see if I can share it again. All right, now we can take a quick look at the properties of the positive rays. Or the anode rays. So they also travel in straight lines. How did they find it? Similar to cathode ray tubes, when they place an object in the path of these canal rays or the positive rays, they could see a shadow, can see shadow, the shadow formation. And the positive rays also have a momentum. Positive rays also have a mass and a kinetic energy. How did they find out? With the experiment with a paddle wheel. The paddle wheel spins. And also they know that the positive rays or the anode rays, they are positively charged. they did an experiment with charged plates, and the positively charged anode rays, they deflect towards the negatively charged plates. You can recall that in the cathode ray experiment, cathode rays deflected towards positively charged plates, but in the case of anode rays are going to deflect towards the negatively charged plate. So it's going to deflect towards negative plate. And most importantly, now you can see the first 3 points I have written here. They are pretty similar to what you observed for cathode rays. The main difference is when it comes for the EM ratio. For the cathode rays, no matter what gas you fill, no matter what kind of cathode material you use, the EM ratio didn't change. However, in the case of positive rays or the anode rays, the EM ratio is going to change. It's going to depend on the type of gas you have in the tube. Change with the type of gas used. So the nature of this the anode rays is dependent on the type of gas we have. Now this is like a very important point in your exams. If they give a question like related to these cathode rays and anode rays, they will try to see your understanding. They will try to see that you know for the anode rays, EM ratio changes, but for the cathode rays, EM ratio does not change. And additional experiments on this topic in anode ray experiments, further experiments found that they get the lightest positive charge, the lightest positively charged particle when they use hydrogen. Now this is not an actual property. I'll just put a note here. You get the lightest positively charged particle was obtained when hydrogen was used. So that is an additional fact. It doesn't come under the properties of the positive rays. The properties of the positive rays are these first 4 points I have mentioned. Okay. Now let's move on to the next part. Now in your syllabus, the next name that comes is Henry Becquerel. Henry Becquerel's name is associated with the discovery of radioactivity. So Henry Becquerel is credited for the discovery of radioactivity. Ernest Rutherford further did more experiments with radioactivity, and Ernest Rutherford found that there are 3 types of radiation types. There are 3 types of radiation. The three types are the alpha rays, beta rays, and the gamma rays. So in his experiment, he used a radioactive substance. This purple item you see in the box is the radioactive item. So he put this radioactive substance in the box, and there is a small opening. So it's like a gun shooting radiation. So when it shoots these all types of radioactive particles, there's a small slit. So when we have a small slit, we can get a beam of particle in the shape of that slit, the slit. And once he get this beam of radiation out from the slit, he subjected that radiation into magnetic field and also electric field. So he provided first an electric field. He found that there is one type of particle that deflect towards the negatively charged plate. Now you can see the negatively charged plate here, and you can see the alpha rays. Alpha rays are attracted towards the negatively charged plate, making him to think that alpha rays are positively charged, and also it is a particle. When we say a particle, that means it has a mass, like a rock or a sand grain. When it is a particle, we think about mass, that there is some sort of a mass in it. And then he noticed there is another type of radiation that is attracted towards the positively charged plate. So if something is attracted towards a positive charge, that something should be negatively charged. And then he found these beta rays, they are negatively charged. And also it is also a particle. If it is a particle, it can be blocked. Like think of a ball. If you hit a ball to a wall, it's going to bounce. The wall can stop the ball. Why? Because the ball has a mass and ball cannot go through the wall. So same way, if something has a particle nature, it can be stopped by a barrier. So beta rays are also particles. So now beta ray is found as a positively charged particle. And then gamma rays, it did not deflect in a magnetic field or in an electric field. And he found these to be some high energy radiation. They have no charge. And also it is not a particle, it's instead high energy radiation. So those are findings of Rutherford. Radioactivity first discovered by Henry Becquerel, but Rutherford did further experiments and going into finding 3 different types of radiation. He didn't stop there. He continued with radiation. And now this is a very important piece of experiment that is constantly asked if they are going to ask anything about these experiments. This is what we call as the Rutherford's the gold foil experiment. So in this experiment, he had the radiation source. Here he has his radiation source. And you can see there's a hole. So this radiation is shooting out. So his radiation this time, it is not a mixture of alpha, beta, gamma. What his radiation source issued is alpha radiation. Just alpha particle. So these alpha particles are being shot at a very thin gold foil. So this gold foil is really thin, really thin. And he placed this fluorescent screen all around this gold leaf. What he observed is that major part of these alpha particles, majority of alpha particles went through this gold leaf. And since this screen is fluorescent, he can see where the particle hit. So the particle, even though it was a particle, it was able to go through this gold leaf because it was very thin. The gold foil was very thin. So it's like it can break through this gold foil and go in. And then he noticed that there are some alpha particles that actually deflected with a very large angle. You see these particles, alpha particles, they have a very large deflection. This one, they deflect in a large angle. And then there were very few particles that bounce back all the way the other side of the gold foil. So these are the three observations. So in Rutherford's gold foil experiments, there are three main observations. Now we are going to look into what these observations are and what they are going to mean. So I mentioned that when alpha particles are shot at the gold leaf, majority of these alpha particles, they went through the gold foil. So the first observation is that majority of alpha particles go through the gold foil. If this particle, something with the mass, something that is dense, can go through a metal sheet, that means there should be some small hollow places in this metal sheet. Like, let's say you are throwing a ball at a wall, and if there is a big hole in this wall, there is a possibility that your ball can pass through the hole. So it is that kind of a scenario. So what he concluded with this observation is that his conclusion that the atom must be mostly empty space. So that is his first observation and the conclusion. And then he saw that there are some alpha particles that deflect with a large angle. So the second observation is that some alpha particles deflect with large angle. This is the observation. Now he knows the alpha particles are positively charged. He knows from his previous experiments that these alpha particles have a positive charge. And if a positive charge is rejected or repelled by something, then that something should be a positive charge as well, because you know similar charges repel, opposite charges attract, similar charges repel. So he concluded this, there is something here, something in the middle, and that something should be a positive charge. So his conclusion is that there is something positive in the center. Something positively charged in the center of atom. And then his third observation is that the alpha particles bounce. So you saw this alpha particle bounced back. What does that mean? Again, think about throwing a ball to a wall. When you hit the wall with a rubber ball, the ball bounces back. Why? Because the wall has some mass, it has some density. So we know alpha is a particle. I mentioned earlier that Rutherford found out alpha particle is not just a charge, it is also a charged particle. So it's like your ball, which is a particle being hit on a wall, and the ball bounces back because the wall is solid. So the third observation is now this bouncing back is shown by very few particles. Remember, in the first observation, majority of the particles go through. In the second observation, some of the alpha particles deflect with a large angle. In the third observation, very few number of particles. Bounce back. So with that observation, he concluded that there is something dense meaning something with a mass in the center of the atom. So these are the three main observations and the conclusions of this. So to get an idea about relative sizes, just assume that we have this Indian gooseberry, or as we call Nelly. You take this fruit and place it in the center of this playground. You can see how tiny these people are. I guess you can see some people here and there. So you can see how tiny people are, and then you can imagine how tiny this gooseberry would look like if you place it in the center. So this fruit is, consider this fruit as the nucleus. And if this is the nucleus, this whole empty space is rest of the atom. So this is what the idea Rutherford came up with, that the atom is mostly empty space. So something very dense. It's dense because there's a mass. You know what density is. You have done some calculation, I think, in all of us. So what is density? It's mass divided by volume. So nucleus, we know it has some sort of a mass, but it is so tiny, such a small space. So if that's the case, the density is going to be very big. So the center is very small but very dense. Rest of the area of the atom is just big empty space. So this is the model he came up with. The Rutherford model, you have the nucleus in the center. He came up with the idea of the nucleus. So the idea of nucleus is brought by Rutherford. He brought the idea of nucleus and nucleus in the center, and the electrons, they are outside. So this is the Rutherford model of the atom. Later, another person did some other experiments with these particles. So the next name we are actually going to come up with is James Chadwick. This is the person who is credited for the discovery of neutron. So his discovery was led because people, by this time, people knew that the sum of electrons and protons should give the mass of the atom. So by this time, they knew that mass of atom should be the mass of proton and the mass of electron. So this is something they believed by that time. But suddenly they started to discover that this is not the case. They suddenly started discovering that, that some atoms are much more heavier than this. Heavier than the sum of electrons and protons. So some atoms became much more heavier than the sum of the electrons and protons. That led to do more experiments. So this scientist, he again used a type of a gun-like thing. You know what it means, that you have an alpha radiation source, which is shooting alpha particles like this. And then these alpha particles go and hit a beryllium sheet. Now in Rutherford's experiment, he placed a gold foil, but this guy placed a beryllium sheet or a plate. When this hit the beryllium plate, he noticed that another type of particle emit from this beryllium plate. These particles emit from the beryllium plate. Now they started doing their regular type of experiment. Place positively charged plate and a negatively charged plate. When they place a positively and negatively charged plate in between this, whatever the particles that were issued from the beryllium plate, he didn't see any deflection. So there was no deflection. And then he tried to do another experiment with magnetic field. He placed magnets, provided a magnetic field. Again, there is no deflection. So he found that these, whatever the particles emitted from the beryllium sheet are actually neutral. So in the sense of neutral, he named it neutral. It has no charge and it doesn't show any activity in the presence of a magnetic field. Now, you don't need to, I believe, you are not required to know this experiment in details because they don't actually go into details. But he further continued this experiment in front of these particles emitted from the beryllium plate. Now he placed paraffin wax. Paraffin wax is pretty much like the candle material you have. Candles are made with hydrocarbons. These are hydrocarbons. The name says it. You have hydrogen and you have carbon, lots of hydrogen and carbon. And when he placed paraffin wax in front of these particles emitted from the beryllium plate, he noticed that positive charges come out from this. How did he know they are positive charge? They did their favorite experiment. Put a charge plate. They put a charge plate like this, and they saw the deflection. So these particles emitted from the paraffin wax, they deflect towards this positive, negative charge plate. So they came up with that idea. So they called whatever this positive charge, this as the proton. They identified the particle that came from paraffin wax as the proton and the particle that came from the beryllium plate, this as the neutrons. So much later, after experiments, they found the mass of the neutron. And you can see the mass of the neutron is actually a pretty similar value to that of the proton. Now, next, Niels Bohr. Now, Niels Bohr proposed a very important idea about the structure of the atom. So what he did is that he combined all the knowledge he had from the previous scientist and his own experiments. He came up with the model, like a solar system model for the atoms. So he's the first one to mention that the electrons are in orbits. Before this, no one mentioned it, even Rutherford. What Rutherford said is that there is a positively charged, dense nucleus in the middle, and the electrons are outside. There is this huge empty space where there are electrons. But he didn't specify where the electrons are. But Niels Bohr, he specified these electrons are in orbits, just like in our solar system. The nucleus is like the sun, and the electrons are like the planets in their orbits. Now, furthermore, he proposed that these electrons are moving very fast in these orbits. It's not just that electrons are not just sitting there. They are not sitting there doing nothing. Niels Bohr said that the electrons are spinning very fast. They are going round and round very fast. That electrons are in orbits and also move in the orbit. Now just think for a moment. We know that our electrons are negatively charged. And then we know our protons are positively charged. And our neutrons, we don't have a charge. Now there is some sort of a attractive force, don't you think? The negative charge and the positive charge should attract because they're the opposite charge. In that case, this electron should go and fall into the nucleus. That means electron cannot exist in an orbit like this because the opposite charges attract, and the nucleus, the positively charged nucleus, is going to suck the electron into the nucleus. But that doesn't happen. So how and why that doesn't happen? Why the electron does not fall into the nucleus? That is where he proposed that the electron is moving. When it moves, now this has the attractive force. This is the electrostatic attraction. But just think, when you drive or when your parents drive you, you feel the curve. If you're taking a bend, like think about going to Kandy or Norelli area, you will find plenty of curves, bends on the road. And they give you special notice some places, drive slow. Why? If you drive very fast, there's a possibility that you will go off the bend or the curve. So what is that force? We call that as the centrifugal force. So if we have a certain mass spinning very fast, there is this force called the centrifugal force. So there's a centrifugal force outside, and also there is that electrostatic force attracting it inside. And the strength of the electrostatic attractive force is equal to the centrifugal force. So electrostatic force is equal centrifugal force. So that way, the electron doesn't fall into the nucleus, and also electron doesn't spin all the way out from the orbit. It can stay in the orbit because it moves. So that is why he theoretically proposed. Now, he cannot see electron moving. He used plain logic and used the scientific concept that is known by that time. So with that, he deduced that the electron is in an orbit and it's also spinning in this orbit. Now, after this point, there is another name that we come across, which is Henry Moseley. Now, from his observation, we can come to the concept of atomic number. Now, Henry Moseley is a scientist who worked together with Rutherford, and he observed that the number of positive charges in the nucleus is going to increase by single electron unit. What this means is that every time you increase the positive charge by 1, there will be an additional electron. Let's say you have one positive charge. If that's the case, you will have one electron. And if you end up with two positive charges, then you have an equal increase of the negative charges. So that is what he said. So this is the foundation for the atomic number. All right, now let's try to sum up some of the findings, more like the numerical values we have come across. Now, from all these experiments and findings, what is very important is that they landed on numerical values, not just qualitative observations. They were able to measure certain numbers and also calculate certain numbers. All right. The proton, the absolute charge of the proton is this. You can see the absolute charge is given in the units of coulombs. So when you see that coulombs number, you can see it is the absolute charge we are giving. And we know the relative charge, that is what we give as a +1. And then the absolute mass of the proton is 1.67 10 to the power negative 24 grams. And the relative mass is 1. And in the electron, you can see that the electron and the proton, they have the same absolute charge value. They both have 1.6 to 10 to the power negative 19 coulombs. The relative charge is a -1. And the absolute mass is 9.1 into 10 to the power negative 28 grams. And this is roughly this kind of a fraction. And what do you think the absolute charge is for neutron? There is no charge, and it has no relative charge, and its mass is pretty close enough. There is a slight difference. I haven't shown the other decimal places, but neutron is slightly, very slightly, little bit heavier than the proton, but the first 3 digits are pretty same. Now, it is not important for you to know the EM ratios of these, but just using your brains and looking at these numbers, what do you think would be the EM ratios? E means the charge, and M is the mass. And if you try to put the EM ratios in a column, separate column, what do you think that would be like? For the proton, you will end up with a value like 10 to the power 4. If you divide the charge, this charge, by that mass, you can roughly end up with that number. And for the electron, Now, do you understand why electron ended up with a larger EM ratio? You can see electron has 10 to the power 8 as the EM ratio. Electron has 10 to the power 8 as the EM ratio, whereas the proton has 10 to the power 4, meaning the EM ratio of proton is small. Why do you think? Can you see that the mass of the proton is heavier? Now you're looking at negative numbers, negative exponent. Negative 24 means it's larger than this 10 to the power negative 28. So in that case, E divided by M, your denominator. M is your denominator, the factor under this division line. When your denominator gets larger, your answer gets smaller. Because you have a larger mass for the proton, you can see that you ended up with a smaller EM ratio for the proton. What do you think about neutron? Do you think neutron is going to have an EM ratio? You cannot calculate an EM ratio. Why? Because its charge is 0. So we cannot actually do that for a neutron. Now, let's look into some previous questions from the papers, some past paper questions. Now, from this part, you usually get 2 types of questions. One type is to explain the experiment. One type is that explaining experiments. So what kind of experiments did you come across? There was this gold foil experiment. And there was the cathode ray tube. Cathode ray tube experiments. Cathode ray tubes were done in 2 different ways. It was done for cathode rays and also it was done for anode rays. Now this is the first type of questions you get with these discoveries, like the history part of this atomic theory. So let's see the first question. It's asking you to select the correct statement with regard to particles associated with the cathode rays observed in a cathode ray tube. So the first option. So it's asking about regarding the particles in the cathode ray experiment, the cathode rays. The first option says the particles are uncharged. Is that true? No, particles, no, this one is wrong because particles are not uncharged. We know that cathode rays are going to have a negative charge. And then the second option, they travel from anode to cathode along straight line. Now it is true, it's traveling in straight line. Now this is where they get. These questions are so easy. So sometimes they combine a true fact and a false fact. So you're going to read one part wrong and pick the wrong answer. So yes, they travel in straight line, but does it travel from anode to cathode? No, it does not go from anode to cathode. It goes from cathode to anode. That is why they're called the cathode rays. So the second one is also wrong. The third one, their charge to mass ratio depends on the nature of the gas and pressure inside the cathode ray tube. No, this doesn't happen for cathode rays. This happens for anode rays, not for cathode rays. So this statement is also wrong. Now let's check option number 4. Their direction of travel is affected by magnetic and electric field. And yes, that is true. What is the fifth option? They are not capable of ionizing the gas inside the cathode ray tube. Now that is wrong. The very reason we see that green color is the ionization. So the cathode rays can ionize gas molecules. So in this case, our answer is, the correct option is number 4. Now you can see that it's asking some facts about an experiment. Now this is about the cathode ray experiment, and some parts has mixed up things with the anode ray experiment. Now the second type of questions you get from this part is like the findings and the name of the person. Either the finding is given and ask you to find the name of the person who discovered, or they will give you the name of the person and relate it to their finding. So this is kind of an example like this. It says, consider the following discoveries made with regard to the atomic structure. Positive rays inside a cathode ray tube. The second statement is the radioactivity by certain types of nuclei. Now I mentioned, I stressed it several times. The radioactivity. This is by Becquerel. And who did the positive rays experiment? It was done by Goldstein. So your correct answer option is number 5. And you can see how very similar names are used. It is very easy to pick Rutherford. What did Rutherford do? He's not about radioactivity. Rutherford is about alpha, beta, gamma. He didn't discover radioactivity. He did further experiments with radioactivity, and also he did gold foil experiment. And yeah, so you see, it's very important that you remember these names and their discoveries, and it is very easy to forget them by the time you are done with the 14th unit in this syllabus. Now this is another problem from a previous paper. I think this is 2015. Now in this one, it's asking, the plum pudding model of the atomic structure was founded by. So who proposed the plum pudding model? It was proposed by J.J. Thompson. So now you have an idea what kind, the nature of the questions you get from this part. And you might be wondering why I didn't go into the other parts, like Albert Einstein's part. It comes together with the next section, like which we would be doing in a second part, which talk about the wave nature of matter. But just to continue, since we have a little bit more time, I will walk into the next part. Now, you can remember that Henry Moseley laid out the first idea for the concept of atomic number, that the numbers increase by 1 electron unit. So much later, these things were well developed, and we came up with the idea of the atomic number. Now, what is atomic number? Atomic number tells you the number of protons in an atom. This is the number of protons in atom. And you might find it very weird that we use the symbol Z to symbolize the atomic number. Now, when you read the resource book, you will see certain origins of certain scientists. Some of them are German, French, Danish. So when people discover something, they tend to put a word or a symbol that origin from their native language. So this is something related to German language. So that is why we ended up Z for the atomic number. So this number of protons, or this atomic number, is something like an ID number. Two people cannot have the same ID number. It's just like that. It's unique. It's an identity of the element. Atomic number is an identity. So two elements cannot have the same atomic number. Now, if our atom is charge neutral, that means because everything and the charge is neutral, we should have the same number of protons. So for a case of neutral atom, what we call as a neutral atom is there is no charges, not an ion. In a neutral atom, the atomic number is same as the number of protons because it is charge neutral, there are no charges, then in that case, it is equal to the number of electrons. Now that is for a neutral atom. Now you cannot do this game for a charged ion, because in a charged ion, you will have a different number of electrons. All right. So this is the atomic number. Now, J.J. Thomson's name is popping up kind of all the time. J.J. Thomson is a scientist that did a lot of other experiments, and together with another scientist named as Francis Aston. Francis Aston and J.J. Thomson. Together, they developed a device and a small instrument called the mass spectrometer. As the word says, it has something to do mass. Now this mass spectrometer is a device that can separate elements by mass, separate atoms or particles by mass. This can separate particles by mass. Now with this instrument, they were testing different elements and they noticed that the same element can give different masses. They observed same element give atoms with different masses. Now this gave the start for the discovery of isotope. So they together worked to discover isotopes. Now let's take a small look into what isotopes are. Isotopes are atoms of the same element. They are atoms of same element. But the atoms have different masses with different mass. So for example, we can take, you are already familiar with carbon isotopes. We have carbon, the atomic number, we can write it as this. So when we write a symbol of the element, the atomic symbols, we have the symbol of the element. And then we put the atomic number. This is and I still didn't come for the mass number. We put the mass number here. I will come into what mass number is in a while. So in isotopes, they have this atomic number 612. We can write the same atomic number 613 and the atomic number 640. Now, since the atomic number, this is the atomic number, they all have the same number of protons. They all have 6 protons, and you don't see a charge, so they are neutral atoms. So in a neutral atom, the number of electrons and the number of protons are equal. They have the same number of electrons. And the difference is the number of neutrons. In the C12, you will find 6 neutrons. C13, you have 7 neutrons, and C14, you have 8 neutrons. So in the case of isotopes, The reason for different masses is because they have different numbers of neutrons. So that's the reason why there are same atoms of the same element, but they're going to have different masses. Now, let's see what I mentioned here. What is that? The mass number. Let's take a look at the mass number. You get the mass number with the sum of the number of protons, that is the number of protons plus the number of neutrons. Mass number is symbolized by the symbol A. And the number of protons is same as the atomic number, which is C. So it's pretty much like A equals Z plus neutrons. Excuse me when I say Z, because I'm kind of, when I started using American students, I ended up using Z instead of Z because they don't understand what Z is. Now I'm having a hard time switching back into Z. So if I say Z, it's pretty much the Z I'm talking about. All right, so this is an important relationship. I believe you are familiar with doing small calculations with these things. You probably have done a lot of things with in your O-levels. Next, I would walk into the atomic mass scale. So let's go into now, we know certain numerical values about electrons. We know the mass of electron, mass of proton, mass of neutron, and overall way to calculate the mass of the atom. But why do we need another different type of scale? The reason is, if you can recall, the masses, they were not very simple numbers. You had to deal with numbers like 10 to the power 24 or negative 24, 10 to the power negative 28, that kind of numbers. Now, this is not very easy to deal with. So we actually needed something a little bit more simple. So we have developed, for simplicity of use, different scales. One scale we are going to talk about is the unified atomic mass. Another scale we talk about is the average atomic mass. Another scale we are going to look into is the relative atomic mass. or sometimes simply called as the atomic mass. First, we'll look into the first one I have mentioned here, the unified atomic mass. So this unified atomic mass, we use U as a symbol. If you flip through old books, you will also find AMU as atomic mass unit. So earlier it used to be called as AMU. This is the old version, but the new version is unified atomic mass. We simply use U. So this is defined as, so 1U, or the unified atomic mass, is defined as 1/12 of the atom of C12 isotope. So to make a little bit more sense, you take mass of one atom of the C612 isotope. So you take just one atom from this C12 isotope and divide it by 12. Now what do you think is the mass of one atom of C12 isotope? I know that you have done some calculations with mole. You know what a mole is. 1 mole is equal to an Avogadro number of things. So what is the Avogadro number? It is this. That is the Avogadro number. If you take this many carbon 612 atoms, this many atoms are going to weigh exactly 12 grams. So if you take Avogadro number of C12 atoms, it's going to weigh, that Avogadro number of atoms is going to weigh exactly 12 grams. Now this is the mass. If you divide 12 by Avogadro number, you get the mass of one atom. And now you have to divide it by another 12, this 12. So divide this whole number again by a 12. So that gives you the atomic mass unit. So this number ends up being 1.66. There are some numbers. I'm not going to write everything. 10 to the power -24 grams. So that is what 1U, or one atomic mass unit, is. 1U is equal to 1.66 10 to the power -24 grams. Now what we do is we measure everything with respect to this number. It's pretty much like, think this dividing one atom of C12 isotope. So I'm going to erase this part. Let's say this is our carbon atom. That's our carbon atom. And I'm going to divide it into 12 equal parts. I'm going to divide this carbon atom into 12 equal parts. Hopefully I have 12 parts. Let's see. I have 1, 2, 3, 5, 6, 8, 9, 10, 11, 12. So this is it. One carbon atom. I have my one atom and I divided into 12 parts, and I'm taking one part. Let's say I'm taking this part. Now this is what my U is. That is what this definition means. You have one carbon atom, divide it into 12 equal parts and take one part. And now we measure everything with respect to this part and see how many times we have the other things. It's like, think about a pizza. You have a large pizza, you divide it into 12 equal pieces, and you have this slice. And then you can, this one slice. You can measure anything with respect to this slice. You can measure the weight of your book with respect to this slice. So let's say you put your book, you have a balance. You have a balance. You put your book on one side, and on the other side, you put your pizza slice. Let's say you have to put 2 pizza slices. So that means your book is equal to 2 slices of pizza. So it's like that. We are using that 1/12 part of the carbon atom as a measuring unit, like a standard unit, like a meter ruler or 1 gram unit. So that's what the idea of this unified atomic mass is. All right. Next, an important thing, sometimes students get confused with 1U being 1 gram. Sometimes instead of, let's say, the carbon atom, if we take carbon atom, we say it is 12U. So how did we ended up with that? We have another relationship. We say that 1 gram contain an Avogadro number of U's. What is the Avogadro number? That is 6.022 into 10 to the power 23 U. That means like having Avogadro number of pizza slices is considered as another unit. So when you have an Avogadro number of unified atomic masses, that is considered as 1 gram. And that is how we end up seeing the carbon's mass given as a 12 gram. But we'll be looking into this in more details as we do chemical calculations. So as we do this, you will have a better idea about this atomic mass unit and its use. Next, we'll try to see if we can finish the average atomic mass. Now, this one I talked here is about the first one, unified atomic mass. Next, we'll look into the average atomic mass. Now, let's say average atomic mass. Let's say we have two atoms. The first atom has 5 protons. Let's say the first atom has 5 protons and it has 5 neutrons. That's our first atom. And our second atom, we will say it has 5 protons and 6 neutrons. So if the number of proton is 5, what does this mean? What is this number? Number of protons tell you the atomic number. So you can see they both have the same atomic number. Now let's find what their mass number is. Their mass number is the number of protons plus the number of neutrons. So the first atom's the mass number is 10. The second atom's mass number is 11. Now you have to know that the mass number is always a whole number. Mass number cannot be a fractional number. Why? Mass number is the sum of protons and the neutrons. Mass number is the number of protons plus the neutrons. You don't have fractional protons. You don't get half a proton. You don't get half of a neutron. They are always whole numbers. So when you add two whole numbers, you should get a whole number. So mass number is always a whole number. Now, a while ago, we learned about the unified atomic mass unit. So according to that, we have to know that one proton weighs 1 unit or one unified mass unit. If and also one neutron is also one unified mass unit. So that means if we have 10 of a total of a such unit, then we can rewrite this as 10U. The same way for the other atom, we can write as 11U. Now, if you go into the periodic table and check the atomic number 5. I don't know if you have a periodic table with your hand, but if you check it, you will find the element holding the atomic number 5 is boron. So in the periodic table, you will find boron, atomic number 5, and you will find a mass as 10.801. So this is the mass. Now you might be confused that earlier I showed you the atomic symbol where you put the atomic number Z down here and mass number here. But when we show things in the periodic table, we show it a little bit differently. So if you see a whole number is going to be your atomic number, and you will not see a whole number for the mass, because the mass given in the periodic table is not the mass number. It is rather the average atomic mass or the relative atomic mass that is given. So now we are going to see how we ended up with this 10.8. what is the normal way of us taking the average? Usually when we take average, if I ask you to take the average of 10 and 11, the average, you take it by 10 plus 11, divided by 2, you get 10.5. So is that the average we see in our periodic table? No, we don't see 10.5, we see 10.801. So how did we ended up with this? We ended up with that number is because if we examine the abundance of elements in our nature, they are not equally abundant. When it comes for boron, boron has two isotopes. One isotope is boron 10 and the other isotope is boron 11. So in nature, we have boron 10, 19.10%. This is the abundance. That means if we take 100 boron atoms, 19 of them are going to be boron 10 isotope, and the rest is the boron 11 isotope. And in nature, we found boron 11 to be 80.10% abundant. So now, if we do the mathematical calculation in a different way, so boron 11, we have 80%. So I'm going to multiply 11U by 80%. And I'm going to use the 100 as well. Now that is one part. Plus, my next part is I'm using the numbers for boron 10 isotope, which is the 10U multiplied by its abundance, which is 19. I'm using the 100 like that. And if you do this math, now you are going to end up with this number you see in the periodic table. So now you will end up with 10.801. If you want, you can use U. If you want, you can use grams. So now you saw a very different way to find average. When it comes for finding average atomic mass, we use a different method. Usually we add the two together and divide it by 2. That is the usual way of finding average. But here, that is not how we do it. We consider the abundance, the natural abundance of the isotopes. So how do we calculate it? We calculate it by the average atomic mass. Average atomic mass, we calculate it with the sum. I'm going to use sigma of the isotope mass. Multiply it by fractional abundance. What did I call by fractional abundance? This 80%. I'm writing it with the 100. If you don't want to write it as 100, you have to write it as 0.8010, not as 80%. So what this means is that you take isotope 1, the first isotope mass, multiplied by its fractional abundance, and then add, keep adding the second isotope mass you multiply its fractional abundance. So that is what we call as the average atomic mass. Now we are going to do a lot more calculations in this, but I was just laying out the background for the concept that you have to know. When we come to find the average atomic mass for atoms, we do not use the regular average calculation method. We use a special technique where we consider the fractional abundance. So if you have the abundance as a percentage, you use it as a fraction. You have 80%, you use it as 0.8. If you have a 20%, you use it as 0.2, because when you divide 20 by 100, you get a 0.2. Now, for the sake of completion, we are pretty much at the time of ending. So the last one I think I had in this atomic mass scale is the relative atomic mass. Or what we simply call as the atomic mass. This is basically a ratio between the average atomic mass and the unified atomic mass. So this is a ratio of average atomic mass and unified atomic mass. And we call this, because it is a ratio of two masses, what do you think at the end? Are there any units? No, this has no units. So this is like a dimensionless physical quantity. Why? Because we take ratios, we divide the mass by another mass. So if you're using grams to grams, they cancel off. If you're using U to U, they're going to get canceled off. So what does that mean? If you're showing the average atomic mass, that means if I'm showing average atomic mass of boron as 10.801 U, I can show my relative atomic mass of boron as simply as 10.801 without the unit U. Why? Because I'm dividing 10.801 U with 1 U. So U to U cancel out. So the relative atomic mass ends up without unit. So that's all for today. I hope you were able to